So now that we have seen internal energy, we have seen work, we have seen heat, the last thing we can talk about then is finally the first law of thermodynamics. So what is the first law of thermodynamics? Well, basically, the first law of thermodynamics is just conservation of energy. So all it says is how many different ways can I change the internal energy of my system? So, for example, we know we can change the internal energy of our system if the heat flows into the system. This is the specific heat that we've been talking about. So in that case, if I have heat flowing into the system where it is absorbed, then I'm going to get a positive change in internal energy. So basically just meaning either I'm going to increase the kinetic energy or I'm going to change the potential energy, things like that, but I'm going to get a positive change. So if heat flows into the system, meaning that this is positive, then this is going to be positive as well. Well, we can also do work, right? Now we can do work either by the system or onto the system, and the way that we're going to write about it is the work done on the system. So in this case, this is going to be the work done on the gas, or at least on the system, not the work done by the system. Now again, the difference between the two is that this one comes with a negative sign, the other one just simply had a positive sign. So what this one says then is that what? If I use my system to do work, or if I do work onto my system, in that case if I do work onto the system, then the energy is then going to change. So if I have a positive work done on the system, meaning that here I'm doing work onto the system, ultimately what that means then is that this work is going to be negative because I'm compressing my system, which means that I have lost energy. So this is simply the first law. So the first law of thermodynamics simply is conservation of energy. It simply means that to change the internal energy, I'm either going to have heat flowing into the system, or I'm going to do work onto the system, or the system itself do work. If the system itself does work, this will become positive. But if I do work onto the system, then it's going to be negative. But ultimately, to get the internal energy to change, this thing then has to, well, I'm either going to do work, or I'm going to have heat flow, or I'm going to have both, right? So if I write this out, this is then going to be Q minus then the pressure times the change in volume, if I have a constant pressure. So this is just the first law. So again, the first law is simply conservation of energy. That's it. But it gets its own fancy name. We'll find out a lot. So somebody just applies conservation of energy to something and then it gets its own fancy name. But anyways, that's all it happens to be. Now there are particular thermodynamic processes that we're typically going to see. So let's start talking about some thermal processes that we'll see on a regular basis. So thermal processes. So the first thermal process is what's known as isobaric. So an isobaric process is when the pressure, using a little p, is equal to a constant. Okay. So on a PV diagram, what that'll look like is, so if this is V and this is pressure, simply this is going to be some flat horizontal line. Right? So this is happening at some constant pressure. So whatever this initial pressure is, whether this thing is increasing or decreasing, just means we have constant pressure. So this is our isobaric. In this case, there is work done. The work done is simply then going to be the area under this curve, right? So in this case, this will represent the work. Our second one is that isovolumetric that we talked about. Volumetric. So again, isovolumetric simply means that the volume is equal to a constant. So in this case, if I look at my pressure versus volume, in this case I'm going to get some sort of vertical line. So I'm going to get something like this. I can actually draw straight. There we go. So this might be either decreasing pressure or increasing pressure. It doesn't really matter. Ultimately, it's just going to look this way. All right. Now, in this case, as we talked about here, since the pressure is changing but the volume is not changing, that means that there is no work done. So in this case, we know that the work must be equal to 0, which means by the first law of thermodynamics, the change in internal energy is simply going to be equal to the heat. That's it. Okay. So in this case, since the work is equal to 0, change in internal energy is just simply equal to the heat. The third one we're going to see is what's known as isothermal. So isothermal simply means that the temperature is equal to a constant. So in this case, if I plotted my pressure versus volume, so in this case, this thing is going to look something like this, okay, where this guy's going to represent some temperature, but I could have a different line. I could have something that looks like this, right? So in this case, if this one was at temperature T1, this one was at temperature T2. In this case, T2 is greater than that of T1. So the further this thing is pushed away, the higher the temperature happens to be. Next one is what's known as adiabatic. Adiabatic. So adiabatic is a system that changes either so slowly or so rapidly that it's always quasi in equilibrium. Okay? So basically what happens here is that the heat flow is equal to 0. Okay? So basically meaning that there is no heat exchange from whatever externally is working on the system. So basically this is what we call a quasi static. So if I was looking at a PV diagram for this guy, it looks fairly similar to this one, but it's a lot sharper. So basically this thing's going to do something more like this. So this is what we know as adiabatic. So in this case, again, what it means is either the system is changing so slowly that the system will always basically be in equilibrium. So it changes in such small increments that it's roughly in equilibrium basically the entire time. Or it's changing so rapidly that it happens so quickly that the system doesn't have, or the external system or whatever it is, doesn't have time to respond, so it just jumps to exactly what it's going to be, with basically, again, no heat flow because it hasn't had time to actually respond, it hasn't had time to do anything. And finally, the last one we're going to be interested in is what's known as cyclic. So for cyclic, all that means is, again, if I look at my PV diagram, it does exactly that. It means it starts off at some point A, it's just going to go around some sort of closed loop and end up back at the same exact location. So this is what we call cyclic. So in here there is work done. There is going to be work done. That's going to be here, that area under the curve. But what happens here is that there's no change in internal energy, which basically means that if it starts off at point A, it has some sort of, again, kinetic energy, potential energy, goes through some sort of process, but goes back to that same initial position. In that case means that what? That it starts and finishes with exactly the same amount of internal energy. So here, the change in internal energy must be equal to 0, which means by our first law of thermodynamics that our heat must then be equal to negative of the work done on the system. So these are our typical thermal processes that we're going to be looking at, and more specifically, we're going to look at these thermal processes for ideal gases. So let's talk a little bit about some ideal gases. So let's now put this for an ideal gas. Good. So let's start off with isobolometric. So for isobolometric, again, here we know that the change in internal energy is equal to the heat. This is going to be equal to, well, the heat in this case is basically going to be like specific heat, but this is going to be equal to the number of moles times what's known as CV times then the change in temperature. So CV here is what's known as the molar specific heat at constant volume. So this is molar specific heat at constant volume. Okay. So in this case, our change in internal energy then will only be related to the change in temperature. Again, basically the same idea as specific heat, but here we're going to do it in terms of the moles. So you're going to do it per mole instead of basically per atom, and we're going to hold that at constant volume. For isobaric, we're basically going to get something that looks very similar to it. So for isobaric, here we're going to get that the change in internal energy is equal to the number of moles again times Cp times the change in temperature, where Cp is what's known as the molar specific heat at constant pressure. Now it turns out that the molar specific heat at constant volume is related to the molar specific heat at constant pressure. So it turns out that Cp is equal to Cv plus R, where R again is that universal gas constant. So in this case, it'll always be true that the molar specific heat at constant pressure will be greater than the molar specific heat at constant volume, because you're adding on this extra term of 8.31 with some units. Good. So let's talk about isotherms. So isotherms are a little bit more complicated, so I'm going to erase some stuff here. Well, going back, so what we know then is that what? The change in internal energy then is going to be 0 because, get rid of the adiabatic here too, because the change in internal energy only depends on the change in temperature. Because in this case, we're talking about ideal gas, so they're only interacting gravitationally, so I'm not going to change the potential energy, I'm only going to change then the temperature. So in this case, for isothermals, what we know then is that the change in internal energy will be equal to 0, which means that again, that the work done on the system, negative-wise, will then be equal to the heat flow. So this is going to be my expression. So what this means then is that what heat is going to be equal to negative of the integral of the pressure integrated over the volume. Right? Since this is an ideal gas, this has to satisfy the ideal gas law, which means that the pressure times the volume must be equal to the number of moles times the universal gas constant times the temperature, which means that the pressure is simply equal to N times R times T divided by the volume. So I mentioned this in the previous video, but here, so the pressure is in fact a dependent variable on the volume. So this is going to make this guy positive, so it's going to be equal to then the number of moles times the universal gas constant times the temperature, where this temperature is equal to a constant, times the integral dV over V from then the initial volume to then the final volume. So if I integrate this guy, this is going to give me a natural log, so I'm going to get N times R times T times the natural log then of the final volume to then the initial volume. So in this case, what I know is that the heat flow is then equal to the number of moles times the universal gas constant times that constant temperature times then the natural log. So in this case, if you're told that you have an isothermal process going from, say, point A to point B, you automatically know this is the heat and this is equal to negative the work done on the gas. So by simply calculating this, you know the two things, and you also know the change in internal energy is equal to 0. So the last thing we want to talk about then is that last one, number 4, which is the adiabatic process. So let's talk about what happens with an adiabatic process. This one's going to take a lot more math, but it'll be fine. So for, again, adiabatic. So again, adiabatic, we know that Q is equal to 0, right? Which again means that what? The change in internal energy must then be equal to minus the pressure times the change in volume. Okay. So here, again, I'm writing in the fact that the pressure can be dependent on the volume, which means that, again, we're going to look at the differential change of the volume. So take it in small increments, and then this is the differential amount of energy change for that differential amount of volume change. Now, here, we know this is then going to be equal to what? The number of moles times the specific heat at constant volume times then the differential amount of change of temperature is then equal to minus the pressure change times this guy. Mm-hmm. So, we'll leave it that way for now. Actually, I'm going to divide both sides by this. So I'm going to get N times dt is equal to minus P over CV times dV. Okay. Now, what I also know is that this has to satisfy the ideal gas law. So again, remember the ideal gas law says the pressure times the volume is equal to the number of moles times universal gas constant times the temperature. And now let's take a derivative of this entire thing. So let's go ahead and do that. It's getting a little dark in here, so we'll turn that on. So here, both of these are changing slowly, so it's going to be the same thing then as the change in pressure times the volume, plus then the pressure times the change in volume must be equal to the number of moles times universal gas constant times then the change in temperature. So now, I'm going to solve this then for n dt because I want to replace this thing here. So now, let's divide everything by r. So this is going to become dp times v plus p dv, all divided by r, is equal to n dt. So basically, all I'm going to do is I'm going to replace the number of moles times the differential change in temperature, which is what this is, by simply this other side. So let's do that. So this is now going to become, what? So I'm going to bring the r, I'll do that. Let's do small things. So I get a dpv plus pdv, all divided by r, is equal to minus p dv divided by cv. Okay. Now, let's multiply both sides by r. So finally I get a dpv plus pdv is equal to minus r divided by c times pdv. Right. Now notice here I have a p dv, here I also have a pdv, so let's bring this to this side, and then let's rearrange everything. So finally, we're going to get then is that what? I get a v times dp plus, I'm going to get a 1 plus r over cv is then equal to, oops, sorry, p times dv is equal to 0. Right? Good. Okay. So now we're going to go ahead and divide everything through by p times v. And then finally we're going to rewrite this thing as then what? So the other thing to note is remember that r is equal to what? CV. So let's see here. So I get, so remember that CP is equal to CV plus R, which means that this is then CP minus CV. Right. So if I insert that in here, and then let's divide everything through. So finally what we're going to get, skip over to here, is I finally get then that dP over P plus gamma dV over V is equal to 0, where we define gamma then to be equal to CP divided by CV. Now, here, once I finally have this form, I get rid of all this other stuff, we can now simply integrate the entire thing. So let's do that. So now I'm going to get that the integral of dP over P plus gamma times the integral of dV over V must then be equal to 0. So if I integrate this, this is simply the natural log of P plus gamma then times the natural log of V must then be equal to some sort of constant. Okay. Now remember though that if I have A times the natural log of B, that's the same thing as the natural log of A or B raised to the 8th power. So I can combine those two. So this is the same thing then as the natural log of P times V raised to the gamma is equal to, again, that constant. Get rid of a natural log, I have to exponentiate both sides. So finally what I get then is that P times V raised to the gamma is equal to E raised to a constant. But E raised to a constant is simply just equal to a constant. Okay. So ultimately, now, one thing I'll point out right now, if you didn't understand all the math to get me to here, don't worry too much about it. What I want you to know is this. So all this thing says then is that what? The pressure times the volume raised to the gamma, where gamma is the same thing as the molar specific heat at constant pressure divided by the molar specific heat at constant volume, is simply equal to a constant. So that means, again, if I go back to this, PV diagram, if I have an adiabatic process, which is something like this, what that means then is that the pressure times the volume raised to that gamma is constant everywhere along this particular path. So at every single point, this thing must be the same thing at every point. Now, we can also use the ideal gas law to rewrite this thing in terms of then the temperature and the volume. So if I do that, I'm going to find this as the temperature times the volume raised to the gamma minus 1 is also simply equal to a constant. So what this one says is if I don't know the pressure, but I know the volume and the temperature, all this means then is that the temperature times the volume raised to the gamma minus 1, again, must be equal to a constant everywhere along that particular path. Okay? So all that means, again, is if this is my adiabatic process, then the temperature times the volume raised to the gamma minus 1 is also constant everywhere along here. So, why is it important? Well, a lot of these problems that we're going to see, especially in the homework and things on like the exam and the practice exam and all that good stuff, are all going to tell you the particular process going from point A to point B or point B to point C or whatever the part of it is. So I'm going to tell you that, for example, I'm going to expand my system from A to B along an adiabatic process. Well, what does that mean? Well, we now know an adiabatic process simply means that what? Q is equal to 0, right? And this is true and this is true. That's what that tells me. Then I might tell you going from B to C, I'm going to say expand my gas again, but along an isothermic process. Well, in that case, isothermic means that there is no change in internal energy, so I know that's equal to 0. And I also know the work, that's that simple natural log that we wrote down, which is also then equal to what? The heat. So I know both of those things. If I tell you it's an isovolumetric process, well, automatically you know the work is equal to 0, and then you can find everything else from there. So typically, all we're going to do is we're going to tell you the type of process, and then you have to use what it is that you know about the type of process and all of these expressions that we just came up with to then find whatever quantities that we need to know. So that's what you're going to be doing then on things like the homework as well as things like the exam. So make sure you have all of these different thermodynamic processes written down. What's 0, what's not 0, what relationships do you automatically know based off of the type of process that it is. So those processes will tell you what to do when. So in the next video, we'll do some examples. We'll do an example of the first law as well as an example using basically adiabatic processes and all these different things.